Hi, I'm Joshua Jensen with Sunflower Structural Engineering. This presentation will be on beam torsional bracing. This presentation is sort of a continuation of the last presentation I did or video I did on the flexural strength of continuously braced beams. Uh, and the bracing would be on the top flange of the beam, and it's provided by floor joists. So here you have a picture of a beam, and this is the end of the span, and it's supported by a steel column. And that steel column has a top plate over it that is about 3/16 of an inch thick, and it's got these tabs, and the tabs are folded over onto the beam to hold everything together and to hold everything in place. So the question becomes, is this, AISC and the beam strength equations are dependent upon the beam being torsionally braced at its ends. And the question becomes, is this beam actually restrained torsionally? That's kind of what this whole presentation is going to cover. So in this instance, there's bolt holes in this top plate, but there is no bolts in the holes. There is a wall that intersects with the column, however, and so that may end up providing the restraint required for the system. The other source of restraint is possibly even the floor system itself, the floor joists providing some rotational restraint. And then even though this column is not bolted to the beam bottom flange, there is still some capability to provide some rotational restraint just based off of the width of the column and uh, the restoring moment that occurs because of the force that's transmitted between the beam and the column. Okay, here's another beam, and this beam was having some problems. First thing I want you to notice is this column here, how it's offset to the left side. This column is not actually centered under this steel beam, so there's a little bit of eccentricity there already. And then I'm going to show you another picture of that same beam. Okay, so here's that column and the beam that we saw in the last picture. Here is another steel column in the floor above, and it's coming down and it's bearing on this beam here, but the load is not actually centered over the web. It's offset to the side, and it's eccentrically loading this beam to where it's giving it a tendency to twist. Here is the column and the photo above that we just looked at. I got a picture of the base of the column to show how the column was actually secured at its base, and it's really just a very thin base plate, maybe a quarter of an inch thick, maybe 3/16 of an inch thick, with two wedge anchors. There's not much rotational restraint whatsoever. It's basically a pinned connection. Um, this picture, you can kind of see a little bit better how this beam here is twisting because of the eccentric load from this column. Okay, so here's another beam, another example. And remember, the beam needs to be restrained or braced at its end. So here's a little tube column that is actually welded to another steel beam at its base, but it's also got these pour stop plates. These are quarter-inch plates that are welded to the sides of the tube on both sides. So if this thing is very rigid rotationally, very, very rigid. So this little tube column is very, very rigid rotationally in comparison to this beam and should be able to provide adequate rotational restraint. The only question is the web? I'd say the only question here is the web stiff enough, strong enough to uh, to prevent deformation and render the bracing, the torsional bracing, inadequate. Here's another example of a steel beam spanning across a garage, and it's got a steel column support at center. You can see there's no special bracing on the bottom flange. There are ceiling joists that frame into the top flange that laterally restrain the top flange. Um, as many of you will know, over the support, the bending moment is negative, and so the bottom flange is in compression, and the bottom flange is what can buckle in lateral torsional buckling. So you got to ask yourself, what is actually providing lateral restraint in this picture? Is it the joists? Is it the column? Another steel beam. This beam had a little bit of an issue. I believe the city inspector um, wrote this up on an inspection report that this beam was not properly bearing on this column here. And at first glance, it looks pretty standard. You know, that's what the detail normally looks like. You don't see a lot of web stiffeners in residential all the time. A lot of times you see this style of connection. Not very robust, but hey, that's what you see a lot. And anybody that says that you don't see that a lot is probably not out in the field enough. So you can see there's some adhesive here on the bottom of this wood plate. Okay, so they've taken this top plate and they've used adhesive to secure it to the beam, but they've also driven nails into the side of the plate. Right there, you can see that nail. They've driven nails into the side of this wood plate, and they've actually turned them over, or bended them over the top flange of the beam to kind of lock that plate in place. So you see these tabs here. They fold. Usually, you'll see these tabs folded over the beam flange to secure the column to the beam. But for whatever reason, there's no tab on this side. It looks like the top plate was just trimmed off. So you have to ask yourself in this situation, is this beam adequately braced? Well, that's kind of a tough question because there's a lot of factors that come into play. Does this floor system provide rotational restraint to the beam? We know it provides lateral restraint. I think everybody could agree this floor system provides lateral restraint to the top flange of this beam. But where is the rotational resistance coming from? What is stopping this beam from twisting or overturning? And is whatever is stopping it from overturning, is that adequate for the loads that it must support? Well, one thing you got to keep in mind is sometimes these columns aren't absolutely plumb. You know, AISC tolerances are L over 500. So, you know, this column could potentially be out of plumb, and it could be placing an eccentric load on this beam, causing even more twist. So you got to keep those kind of things in mind as well. Okay, so the first thing I want to kind of dive into here is I want to dive into the beam bracing equations in AISC 360-10 Appendix 6, which covers torsional bracing as well as Other forms of bracing, just normal uh, lateral restraint to the compression flange. So torsional bracing can be fastened or applied anywhere on the cross section of the steel beam. It doesn't have to be on the compression flange like lateral bracing does. So in the specification, Appendix 6, they provide you with a formula to calculate the required bracing moment, or in other words, what should I design? What moment should I design the brace that's going to provide torsional bracing? What moment should I design that for? How much torsion or how much moment is going to be required to stabilize my beam, and what should I design the connection for and the brace for and everything like that? So they give you that equation. And then they also give you a set of 3 equations for stiffness. And the first equation is the required stiffness of the brace itself. And what this means is just the actual brace member and its connection to the beam. And it's saying that is what's required stiffness wise in order to be considered an adequate brace. So you can see in this equation, it's actually got 2 other uh, betas in it, beta sub t and beta sub sec. So beta sub t is the required bracing stiffness, not including web distortional stiffness. Okay, so this bracing stiffness is the bracing stiffness that would be required out of your brace if the web of the beam was infinitely stiff and did not have any flexibility whatsoever. In the real world, the web of the beam has some flexibility, and it actually reduces the effective bracing stiffness of your bracing system. So they go ahead and give you the equation, or a equation, to account for that, and that's what this is here. And so this equation has 2 terms inside of these parentheses. So the first term gives you the stiffness of just the web alone, and you can see the thickness. It's thickness of the web cubed over 12, and h naught is the depth of the beam. So it's like they're having you take the depth of the beam, like a rectangular. It's almost like calculating the moment of inertia of a rectangular plate that is the same depth of the beam and the same thickness of the web, and multiplying that by 1.5. Okay, then the second term here will account for a web stiffener. So if you put a web stiffener in, you can imagine your web distortional stiffness would go way, 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 way up, and that's in fact what happens. So there's your web thickness, and then the width of the web stiffener is the term that gets cubed in this formula. So it's basically the moment of inertia of a rectangular plate, that is as thick as your web stiffener and as wide as the web stiffener is. And then of course there's a resistance factor, kind of a safety factor. So this diagram here kind of shows you how the mechanics of this, how I would idealize the mechanics of this beam bracing system. So we're going to say these columns are pinned at the base, because most of the time for residential, which is what I'm trying to gear this video towards, these columns have a adjustable screw at the bottom, and then they have a tiny little base plate with just a few holes for anchors. They're not meant to be fixed. They're meant to just be a pinned connection. Sometimes these posts will get embedded in the basement slab, and there will be some flexural fixity here, but let's just, for the sake of this video, for the sake of this presentation, let's just say these are always pinned, okay? We'll just say these are pinned. Okay, so then at the top, you've got your top plate, and then you've got the beam. Well, when the beam is bending and it's continuous over this column and there's a negative moment, this bottom flange is in compression. It is wanting to buckle, either left or right. It's wanting to buckle. It's lateral torsional buckling. So it's wanting to buckle, and in this case, it's wanting to buckle out to the left. And this column is hinged at the bottom, so it can just freely rotate like this. So there's nothing really stopping this system here from moving laterally to the left or to the right. Okay. Now, if you add in a moment connection or a connection with some fixity to this system, rather than just a pinned connection like here, now it is stable. Now, if this bottom flange tries to deflect laterally, well, you can imagine in order for that to happen, this column would have to bend and rotate, and this beam would have to distort and rotate as well. But this column and this beam both have some stiffness associated with their rotations, so they're not just going to freely rotate. It's going to take some force to make them rotate. Well, that all comes back to these equations here. So the force that you need to design this joint for is going to be M sub RB right here, given to you by the appendix 6. And then the stiffness of your brace and the connection and the beam is all, the required stiffness is all given to you in these three equations here. So that's how a column pinned at the base but fixed to the beam can actually act as a torsional brace for a beam, and you don't necessarily have to rely on the floor system to torsionally brace the beam. So the next question becomes, okay, well, hey, those equations tell me what my stiffness needs to be to brace the beam, but it doesn't tell me what my stiffness actually is. So you have to calculate that yourself, because there's so many different ways a beam can be braced with a torsional brace that you just have to use principles of engineering and mechanics to determine what the stiffness actually is. So we're going to idolize our column as a pinned member here. And we're going to apply a unit moment at the top. We're going to say that's basically the bracing moment, but we're going to only apply 1 kip inch. And then what we're going to do is we're going to try to calculate this angle here. And what this angle is this pink dashed line right here is the deflected shape of the column due to this unit moment. And what I want to do is I want to draw a line that's tangent to that deflected shape right at the end of the column. And I want to figure out what is the angle of that tangent line going to be with the original vertical line of the column. And what that's going to tell me is it's going to tell me how much rotation happens in the column due to 1 kip inch of moment. And so that's actually, if you actually take that 1 kip inch and you divide it by this angle in radians, the units you get for that is kip inches per radian. And that's exactly what a rotational stiffness is. It's kip inches per radian, or kip feet per radian, or force length per radian. Okay, so we're going to say that we're going to call the height of the column H. We're just going to give that H. Okay, so we're gonna solve for all the forces and moments on the member. So 1 kip inch, applied the moment here at the end. So that's gonna force a shear force to be introduced We're pinned at the top and pinned at the bottom. So I take 1 kip inch and I divide it by H, and that is my shear force. And so you apply that shear force at the bottom and the top. 1 kip inch divided by H. Then you work up your moment diagram. You know at the top of your column, the moment is 1 kip inch because that's what you applied. It's pinned up here, but you applied that moment, so you know it's 1. Well, you also know that the shear diagram is constant. If you were to draw this shear diagram, it's just a straight line. So that tells you that the slope of the moment diagram is linear, just another straight line, but on a slope. So and then you know the moment at the bottom is 0, so you just draw a straight line from 0 to 1 kip inch, and there's your moment diagram. Okay, so the area under the moment diagram divided by EI, which is the stiffness, flexural stiffness of the column, that is how much rotation occurs along the entire length of the column. And this equation right here is a little bit wrong. It should read theta equals the integral of the moment over EI times dx. So I messed up on that equation right there, but that's okay. So what you'll do is to get the moment, the area of this moment diagram, which is the integral, it's a triangle. So the area of it, you just do the area of a triangle, 1 kip inch times h divided by 2. So it's a right triangle. So this side times that side divided by 2. Boom, there's your area. So 1 kip inch times h divided by 2. Well, the problem is we don't know how much rotation occurs at the top and how much rotation occurs at the bottom. Well, there's a little trick to that. And the trick is you can use the centroid of the moment diagram to tell you how much rotation occurs at the top versus at the bottom. So the centroid of a triangle is 1/3 of the length of its base, 1/3. So you know that the centroid of the moment diagram actually occurs h over 3, a distance of h over 3 down from the top. So what I do is I take 1 minus 1/3, and I get 2/3. And I say, okay, I know that 2/3 of the total rotation, total change in slope that occurs over the entire length of this column, I know that 2/3 of that will be at the top. And I know 1/3 will be at the bottom. So therefore, I can take that area under the curve we computed a minute ago, 1 kip inch times h divided by 2, and I can multiply that by 2/3, and that is going to be the angle that we've been chasing after this whole time. So 1 kip inch times h divided by 2 times 2/3. That comes out, if you take 2/3 and you multiply it by 1/2, you just get 1/3. 2/3 divided by 2, 1/3, right? So 1 kip inch times h over 3 divided by EI. So then remember the rotational stiffness is a unit of kip inches per radian. So we've solved for this angle that's in radians. So what we want to know is for 1 kip inch of moment, how much did this thing end up rotating? Or for 1 radian, I guess we should say for 1 radian of rotation, what moment would be required to cause 1 radian of rotation? Well, it's a simple thing to solve for. It's 1 divided by theta, which we just solved for. 1 times h over 3 over EI. So it's basically the inverse of this right here. And boom, right there. That is the stiffness of your column brace. It does not include the connection, just the brace itself. Okay, so we have to continue on here, and beta sub TB is the total stiffness of the brace, and that one over beta sub TB is going to equal 1 over the stiffness of the actual brace itself plus 1 over the brace stiffness of the connection. Okay, so we still need to factor in the stiffness of the connection, and that's a lot more difficult to solve for than what we just did. And for this video, I'm going to just kind of leave it there and maybe touch on this later on or in another video on how to determine the stiffness of the connection. Eurocode 1993-1-8 has some guidelines on how to actually do this, but some things you need to keep in mind about the stiffness of the connection is flexibility of the connection between the column and the beam flange will reduce the effective stiffness of the brace. You got stretching of the bolts, local bending of the beam flange, local bending of the column top plate. And here's kind of a little illustration of the beam bottom flange. So this would be your column down here. Here's the column top plate. Here's the beam bottom flange. And then there's a web stiffener here. It's kind of hard to see it, but there's what you can see how as the beam rotates, there's some flexibility in the bottom flange of this beam, and you're losing some stiffness. Okay, continuing on here. Let's go ahead and do a design example. Determine the flexural strength of the beam. The beam is continuously braced along the top flange by floor joists, which provide lateral restraint but no rotational restraint. Design the interior support column to act as a torsional brace for the beam. The stiffness of the connection between the brace and the beam is 150 kip feet per radian. Is a web stiffener required? Choose a Schedule 40 pipe column that has sufficient strength and stiffness to support and brace the beam. Okay, so the beam is a W10 by 12. It's 2 spans continuous, pinned on the outside supports. The interior support is where our column is. Span length is 12 feet 6. The height of the column is 84 inches. And it's A992 steel with a yield strength of 50 KSI and a modulus of elasticity of 29,000 KSI. It's uniformly loaded as well. Okay, so the solution would be, first step is going to be calculate the critical bending stress, and that can be determined using the equation that was defined by Ura and Hellwig for C sub B. And you can find this equation in AISC 360-10 commentary chapter F. It's equation CF1-5. And this equation is for a beam that's continuously braced along its top flange, unbraced along its bottom flange, except at supports. At supports, it's assumed to be braced at the bottom and top flange or torsionally braced. So for our beam with a uniformly distributed load, what it comes out to be for all cases for 2 equal spans under uniformly distributed load is about a 4 1/3. That's not exact, but it's in that ballpark. It's pretty dang close. So then you solve for the critical stress using equation F2-4, which is in the specification, chapter F. It's the critical buckling stress for lateral torsional buckling. And in that equation, you've got your C sub B. So what you have to do is you have to chase down your modulus elasticity, your unbraced length, which for us is 12.5 feet, your radius of gyration about the compression flange, which is it's given in the tables in the steel manual. You can look these up in the steel manual. The polar moment of inertia, or the torsional constant, I guess. Section modulus, the distance between flange centroids, or basically the depth of the beam, almost. So if you solve this equation, plug and chug, you get 74.26 KSI, which is higher than the yield strength. So then I'm going to go ahead and I'm going to calculate the plastic moment. I'm going to take the plastic section modulus times the yield strength, and I get 630 kip inches. Okay, and then I take the section modulus, elastic section modulus, and I multiply it by the critical stress that we just calculated, which was 74.26, and I'm going to get 809.4 kip inches. Well, the bending strength cannot be greater than the plastic moment, so we're going to go ahead and say that the bending strength is 630 kip inches. And basically what this means is that this beam, if properly braced, which is continuously braced along the top flange and braced at all supports, will achieve full plastic moment. If you keep loading it and keep loading it, it will achieve full plastic moment prior to lateral torsional buckling. So next step is determine the required bracing stiffness and strength. Okay, so here's the equation out of Appendix 6 that we just covered. 0.024 times the required moment. For the required moment, we're going to go ahead and use the plastic moment because we're going to say we want to design a brace that will help develop the full plastic strength of this beam. And we could apply a phi factor to this, a 0.9 phi factor, but just to be safe, we're going to go ahead and use the full plastic moment. And then L is the span length, N is the quantity of braces along the span, C sub B is the bending coefficient, which we calculated as 4.33 out of the commentary, chapter F, and then L sub B, which is 12.5 feet for us. So you plug in all those and all those variables, and you get 6.98 kips per inch. That's the required moment in the brace. That's the amount of torsion it's going to take to stabilize this beam and hold it where it needs to be, or the amount of torsion that that AISC is telling us it needs to handle. Okay, so then we're going to calculate the web distortional stiffness using the equation out of Appendix 6 that I showed you earlier. First, I'm going to try I'm going to plug in 0 for the web stiffener component, or the web stiffener term of this equation, and I get 82.1 kip inches per radian. Okay, then I'm going to calculate the required bracing stiffness, not including web distortional effects. So it's 2.4 times the span length times the required moment squared over N, which is the number of braces. We have 1. E, modulus elasticity. IY, which is the weak axis moment of inertia. CB squared, which is our bending coefficient, 4.33. So you plug all these in, and you come out with a required stiffness, not including reductions for the web distortion, of 988.4 kip inches per radian. Okay, so here's where we run into a problem, because the code is telling me I need a bracing stiffness that is 988.4 kip inches per radian. Well, just my web distortional stiffness is 82.1. So what this means is, even if my brace is infinitely stiff and my connection from the brace to the beam is infinitely stiff, the maximum stiffness my bracing system can really actually have is 82.1. And that's way below 988.4. It's not even close. So what this is telling me is that the web will distort, that bracing will be ineffective without a web stiffener, because the web will distort and locally distort, and it will not allow the stiffness that's required to brace this beam. Okay, so web stiffness is inadequate, so we're going to go ahead and try a 1/4 inch thick web stiffener. Okay, so then I go ahead and I calculate the web distortional stiffness again, but this time I include the term for the web stiffener, and what I come out with is, and sorry about all the highlighting here, but what I come out with is 12,898.9. Wow, that is a major difference. We went from 82.1 kip inches per radian all the way to almost 13,000 by adding a web stiffener. So basically, you can say at this point that there's not going to be much flexibility in the web anymore. And all that took was a 1/4 inch web stiffener. So we got rid of that flexibility. Okay, so now we're going to go ahead and solve for the required stiffness of the brace, accounting for the web distortion. Okay, well, it's not going to change all that much really because our web is so stiff now. So we run this equation and we go from 988.4 kip inches per radian, and due to the web distortional stiffness, now it's saying our brace needs to have 1070.4. So it went up a little bit. Required stiffness went up a little bit to compensate for the distortion that's going to happen in the web, but not very much. So 1070.4 kip inches per radian is the required stiffness in our brace and connection together. So let's try a 3.5-inch Schedule 40 column, check the brace stiffness and strength. Okay, so the formula we derived earlier for the brace stiffness, the column stiffness, is 3EI over H. So we run that formula. Remember, for our example problem, we're going to have an 84-inch tall column. E modulus of elasticity 29,000 or 29 ksi, and then the moment of inertia for a 3.5 Schedule 40 column is 4.52. So you come out with 4,681.4 kip inches per radian. Okay, that's quite a bit higher than 1,070.4. So far, so good. But remember, we have not included the flexibility of our connection in this figure here. So we need to figure in the flexibility of our connection. We're not going to be quite this stiff because our connection is going to give a little bit, and it's going to make it a little bit less stiff. If you remember in the example instructions, it said assume that the connection stiffness was 150 kip feet per radian. So if you take 150 kip feet per radian and you multiply it by 12 to convert it into kip inches per radian, you get 1,800. So we're going to go ahead and solve for the stiffness of the bracing system, including the connection. And what you do is you take the inverse of the sum of the inverses of the stiffnesses, basically. So 1 over 4,801.4, which was the column stiffness, plus 1 over 1,800, which is the connection stiffness. And by doing this, you come out with a stiffness that's actually lower than both of the stiffnesses independently. And that's because you're combining the flexibility of the column and the flexibility of the connection, and you're coming up with a stiffness for both of those. And so that's 1,300 kip inches per radian. Well, our required stiffness that we calculated using Appendix 6 equations was 1,070.4 kip inches per radian. We are actually providing 1,300 kip inches per radian, so therefore we're okay on stiffness. That column, that 3.5 Schedule 40 column, can actually act as a torsional brace stiffness-wise for the beam. Now we still need to check the strength of the 3.5 Schedule 40 column. So to do that, we can go to AISC 360, or no, not 360, the manual, and I'm referencing the 2010 version of the manual. Table 4.6. Table 4.6 gives you the axial compressive strength for Schedule 40 columns. And you can look up in that table for an 84-inch long column pinned at the top and bottom. The strength is 60, or design strength is, or design resistance is 64.4 kips. The bending resistance, or the flexural strength, is going to be phi times Fy times plastic section modulus, which is 0.9 times 50 ksi. Oh, there's a little bit of an error there. That should be 35. So 30. So let's recalculate that. 0.9 times 35 times 3.03. So this figure 136.4 kip inches, because most of the time your column's not going to be 50 ksi unless it's a wide flange. For a pipe column, it's going to be 35. So that's going to reduce this number down to 95.4 kip inches. So we know the required moment, strength of the brace, is 6.98 kip inches, which we got that from the Appendix 6 equations. We know that the axial force in the column that is going to be needed is 42 kips. And how you do that is you just take the 630 kip inch moment and you back solve for the uniformly distributed load, which is which actually would come out to be 630 times 8 divided by the span length squared, WL squared over 8, basically. um, and then that'll give you your uniform load, and then you can take your uniform load and multiply it by the length of all the spans, which is 25 feet, and you'll come up with a force. You can multiply that total force by 5/8, because in a continuous beam, a two-span continuous beam that is pinned on the outside supports, it actually works out, if the spans are equal, it actually works out that 5/8 of the load goes to the center support, and then 3/16 of the load goes to each outer support. So we know that we have an axial compressive force of 42 kips. We've got a moment of 6.98 kip inches. We've got a flexural strength of 96.4 or whatever it was. What was that? It was 95.4. Okay, so now let's use equation H1-1 to check the strength of the column under combined bending and compression. So let's take 42 divided by 64.4 plus 6.98, and then divide that by 95.4. And you'll come out with 0.73. So this value here is a little bit off because I used the wrong yield strength here. So this should be 0.73, but it's still less than 1, so it still checks out. Okay. The last thing I wanted to cover is I wanted to kind of go over some FEA models of this beam that we just did a design example of, and I want to kind of visualize and kind of confirm the calculations that we just did, so we can gain a deeper understanding of what's going on here. Okay, so I took the beam that we just did our example on, two equal spans, 12.5 feet each, and what I did is I represented the column at the very middle of the beam with a rotational spring to provide a torsional brace, essentially at the center. And what I did is I started at 1 kip feet per radian, and I ran a model and checked the stability, and then I incrementally kept going up in stiffness from 1 to 5 to 10 to 15 to 20 to 25 to 30, and so on, until the beam reached the plastic moment capacity, which at that point, increasing the stiffness of the beam did not increase the strength, or increasing the stiffness of the torsional brace did not increase the strength of the beam, because the beam began to yield plastically. So that's how that worked. And so the blue points are from a linear stability analysis in FEA. That linear stability analysis did not account for material nonlinearity. The orange points represent the nonlinear stability analysis, which accounted for geometric nonlinearities and material nonlinearities, and some things done to account for residual stresses. And so, as you can see, what happens is as the bending moment gets higher and higher and higher, the difference between the linear stability analysis and the nonlinear stability analysis gets greater and greater and greater, because you start to have softening of the structure due to nonlinear material properties, which is basically portions of the beam yielding and losing stiffness, and also some second order effects where the deflected shape is contributing to the instability. But I wanted to create this chart because I wanted to kind of demonstrate to myself and to everybody that even if your brace or your column doesn't meet the bracing requirements set forth by AISC Appendix 6, that doesn't mean that brace is not contributing to the overall the overall strength of the system. The truth is that yes, up to the bracing, once the bracing stiffness and strength, once it reaches a certain point, yes, any additional stiffness does not increase the strength of the beam element. But when you're below that point, there is actually a relationship between bracing stiffness and flexural strength. So say you run a calculation, you see, oh man, this brace just isn't, it's 50% short of what we need in the code. Well, dang, I can't count it as a brace at all. It's going to do nothing. Well, yeah, to be safe, you'll do that. But in reality, you're going to have you're going to have a considerable boost in flexural strength due to that brace. So I just want to say, even if the torsional brace does not meet the stiffness requirements in AISC, in the real world, the brace can partially brace the beam. In this zone, the strength of the beam becomes a function of the brace stiffness. The chart above shows the nominal flexural strength obtained from FEA for various brace stiffness. The beam used for the analysis was the exact same beam that was used in the design example. Determining the stiffness of the connection between the brace and the beam can be difficult. Eurocode 3 provides some guidance on calculating the stiffness of the connection. Another method is to create an FEA model of the connection, apply a unit moment and get the rotation, or apply a unit rotation and get the moment. Either way, you can do it either way. Being mindful that the relationship between connection stiffness and moment is not linear if the stresses exceed yield. Okay, so that can be misleading if you apply a 1 unit, if you apply a 1 kip inch of moment, and then you get the stiffness, and it's a purely elastic stiffness, but then you're going to design your system to exceed 70% of yield stress. Well, what you haven't accounted for is you haven't accounted for that as the stresses get higher and higher and higher, your connection isn't as stiff as what it is in the elastic range. So what you really need to do is you need to calculate the connection stiffness at the required torsional bracing moment. That's what you need to do. Now, if you're in the elastic zone, if your design is completely elastic, well then yeah, then a unit and 1 kip inch and method will work. One other thing I wanted to go over real brief is, hey, in lieu of relying on the column to torsionally brace the beam, or relying on the floor joist to provide rotational restraint, which is kind of a not necessarily easy. It's not an easy thing to quantify. I believe there's some research out there on it, and there's been, I think it was actually, oh, I can't remember who did it, but somebody did some research on the effectiveness of joists providing rotational restraint to the beam, and it does actually contribute, but it's a hard thing to quantify. So most of the time you just ignore it, because it's hard. If you can't accurately quantify something, it's really difficult to use it for design purposes. So in lieu of relying on the column to torsionally brace the beam, the bottom flange can be braced directly with these type of fly braces or kickers or whatever you want to call them, which is what you see they've done here for this beam. They've got these these braces coming down to brace the bottom flange, coming off of these bar joists. Um, so that's a much, you know, and this just basically solves the problem. You don't even have to think about it. Basically, at this point, stiffness isn't your problem anymore. You just got to check that this 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 brace has the strength it needs. Okay, so next thing I wanted to go over, I wanted to show some FEA. Um, oh, before we get to the FEA models, um, just want to show this one last picture here. It just kind of shows a typical connection detail that you'll see sometimes. Ignore the joist that's been notched. As you can see, this joist here has been cut out and spliced to this joist to make room for this steel column up above. Yeah, ignore that part, but this is essentially the system that we're looking at. Okay, on to the FEA models. So this first model here is just to kind of demonstrate what would happen if you had the steel beam and the column connected to it, but the column was free at the base, completely free at the base, free to move side to side. Still can take vertical load, but it cannot move. But it's free to move side to side. It's not pinned horizontally in any direction. So basically this brace is going to do nothing in this FEA that you're about to see. That this column is going to do nothing to brace the beam at midspan. You essentially have a beam whose unbraced length is the entire 25 feet. And so you can see what happens. This is a stability analysis. So the column just kicks out to the side because the beam is twisting. The beam is twisting at midspan. It wants to use that column as a brace, but the column provides no resistance, so the beam just twists at midspan, and it laterally torsionally buckles at midspan with an unbraced length of 25 feet, and it barely carries any load before it buckles because the unbraced length is so large. So this kind of demonstrates what would happen if the base of the column was free to move. So just want to mention there is a web stiffener in this, but you can see how the beam itself really isn't deflecting at all. See how it's just completely blue? It's really not deflecting much at all because there's hardly any load on it when this happens. When this instability happens. I will also mention that in this model, I included an initial imperfection of L over 500 on the column plumbness. So that 84-inch tall column was a little bit out of plumb, about 3/16 of an inch out of plumb. Okay, this next model is the same thing, except for now our column is pinned at the base like it should be, but we've got no web stiffener. No web stiffener at all. So this model carried a little bit more load than the last model, but because the column was able to somewhat brace the beam, but not very much before that web just distorted. And you can kind of see how that web is just bending. The web is just bending. It's just flexing, and the rotational rigidity provided by the column is kind of just going to waste because the beam is just sort of rotating around the column, and the web is giving way. So right here, right there, you can kind of see the flex in that web. See how it's curved, that curved shape. But you can see there's a lot more vertical deflection in this too at mid-span because this model carried a lot more load. So this brace wasn't completely ineffective, but it did not reach near full flexural strength. Nowhere close to full flexural strength, but it was somewhat effective. And there's how that's the instability. The column kicks out to the side, and the web just flexes. You can see some distortion in the beam flange as well. You can see the beam flange is sort of twisted as well. It's distorted. Another good view. You can see that web flexing. Front view there. Now you can see the beam rotating. You can see it rotating at the top. So if there's any rotational restraint on the top flange from the floor joist, it's going to make this system stronger. Okay, here's the next model. This model is the same thing we just looked at, but this model has a web stiffener. So now we have dramatically increased the stiffness of the web, reduced the flexibility in the web. So now we can really see what that column can do for us as far as acting as a torsional brace. Now we can really see what it can do. You can see the top flange is rotating, the whole beam's sort of rotating, but the column, you can see the column's got some curvature to it. The column is flexing. Yeah, that column's got some curvature in it. It's got a moment in it. But that bottom, you can see the bottom flange along the entire length of the beam is kind of also wanting to just sort of buckle outwards. It's wanting to laterally torsionally buckle. Here you can kind of see how the column is pinned at the base, not fixed. So you can see that column is free to rotate. It's rotating ever so slightly. If that column were fixed, that would provide even more stiffness to this brace. Just another view so you can see what's happening. All that compression in the bottom flange of the beam is causing it to buckle right over the column. Okay, this model is a model without the entire. It's a smaller version of the same model. It just includes a portion of the beam, and there's no web stiffener at all, and it just gives you a clear section view of how the web and the beam sort of just distorts and fails and bends if there's no web stiffener. There's just no flexibility there. This isn't a perfect model, but it's just for illustration purposes, so you can kind of get a grasp of the mechanics. Top flange free to rotate. Bottom flange is fixed to the column, and it just bends the flange. It just bends it. Just not a whole lot of stiffness or strength in that orientation right there. Okay, same type of model, but this one has a web stiffener. This model was kind of useful for kind of looking at the flexibility of the beam bottom flange and the column top plate. Right there, you can see how the beam bottom flange and the top plate are bending. They're flexing, and it's a source of flexibility. Yeah, so you can create these FEA models, and you can use them to figure out what the actual flexibility of that action right there is. See how that beam bottom flange is bending upwards between those two bolts. I've actually got 4 bolts in that connection. So you can see the distortion in the beam bottom flange. You can also see distortion in the column top plate on the compression side. Those are all sources of flexibility. So I hope you enjoyed this video. Oh, wait a minute. I think we got one more. After this model, we got one more model. That's good. That kind of shows the curvature. Really shows the curvature in the pipe column. How the you can really see how the curvature in the pipe column develops. Okay, this model here. It's the same model, but it's frozen right at a point in time that shows the distortion in the beam bottom flange. There's the distortion on the compression side in the column top plate and in the bottom flange. And you can see the curvature of the column, the deformed shape there. So anyway, I hope this video was informative. I hope that you got something out of this. Um, I know I did, putting together this information and kind of studying this problem. And I'm always working on things like this, trying to investigate things and gain a better understanding of the codes and the specifications and all that. So, thanks for joining me.